All right, so we're doing some linear algebra, and we have the following problem. Find the basis for the subspace W of a set of all points x, y, and z such that 3x plus 2y minus 5 equals 0, and this is a subspace of R3. All right, so first of all, let's recall what a basis is. It's a set which spans a subspace or a vector space, and the word span basically means that everything in that subspace or space can be written as a linear combination of the vectors in that basis, and that it's also, second property is that it's linearly independent. Every vector is independent of the other one, meaning that you can't write one vector as a combination of the other ones. Okay, now for this particular problem, for this set, there's a couple ways of doing this. My first solution consists of me just working with this equation, 3x plus 2y minus 5 equals 0, as you can see here, or not with the first line here, or second line in red. And I'm going to actually solve for z. Doing that, you get z equals 3/5 x plus 2/5 y. So this equation, 3x plus 2y minus 5z equals 0, is one equation with three variables, homogeneous equation. It's going to have an infinite number of solutions. The x and y pretty much can be anything they want, but the z's got to be 3/5 x plus 2/5 y. All right. So if you look at all the sets of all the answers x, y, z, they look like x, y, comma 3/5 x plus 2/5 y, right here. And here's what I'm going to do, and I'll explain why I'm doing this in a second. I'm going to rewrite this as a combination of two objects, two vectors. One that has all the x's in it and all the y's. That's what I did here. So x comma 0 3/5 x plus 0 comma y 2/5 y. So I break it up, like, think of it as like the x-y parts in a way. What I did here, the next step after that was over here, I went ahead and factored the x and the y out of that. The reason I did that was because that original set that describes all the solutions to the equation 3x plus 2y minus 5 equals 0 now can be written as a combination of 1 0 3/5 and 0 1 2/5. So what that's telling me is this would be my basis, vectors for my basis. So one of the first challenges is to find those actual vectors, and a lot of the time you have to do some manipulation with algebra, which is what we just did. Okay. And yeah, the x and the y are not needed. They're like constants for us here. We just need the actual objects in the space. All right. So we have our set, and it is spanning and describes every solution. However, you have to show also that the set is linearly independent. And how do I do that? Well, one way is to form a linear combination of those two vectors and set it equal to the 0 vector on R3. So C1, some constant times 1 0 3/5, plus C2, some other constant times 0 1 2/5, equals 0 0 0. And your job here is to try to show that C1 and C2, the only choices for C1 and C2 are 0. Okay, the way you do that is by doing usually a little bit of algebra, like you distribute the C1 and the C2, and you would set up a system of equations based on like adding things and equating stuff over. I think you're okay with that, so I won't go over that. After you do this, you would go ahead and, so I suggest you do that. You would get that C1 and C2 both equal 0. And the third equation these would be the three equations that you get out of that system, by the way. But with C1 and C2 equaling 0, that just tells you right off the bat that this system is going to be, the set is linearly independent. Okay, and therefore, because it's linearly independent and spanning, that set S, which I wrote up here, called it S, is a basis. All right, so solution number 2. The second solution is more geometric in nature. And the way it works is this equation describes a plane in R3. So with a plane, you have these points that you could pick that are on there, okay? And I'll go over why I'm picking points in a second. So 1 1 0 would be 1 point on there, because 3 times 1 plus 2 times 1 minus 5 times 0 equals 0. And I'm kind of doing that at random, kind of like just eyeballing it here. 3 times 5/3 plus 2 times 0 minus 5 times 1 would equal 0. So that's another point. That's my point P2. And then my third point would be 0, 5 halves, and 1. Okay. Now, you might say, is there any other way of doing it besides like eyeballing it? Well, you could pick x and y, and then z, you can solve for z here, okay? That's kind of like what we're doing with the first way, in a sense. We didn't say it that way, but that's what we were doing. And you can try that here, but explicitly using actual numbers. And the reason I did that was because if you have these points on this plane, you can form vectors. So you can form a vector from P1 to P2, and then from P2 to P3. And when you're forming a vector that goes from P1 to P2, the way you do that is by subtracting the like components of each point. So the x's subtracted from each other, the y's from each other, and then the z's from each other. So 5/3 minus 1, 0 minus 1, and 1 minus 0. And that's how I get the 2/3 minus 1, 1. And then from P2 to P3, I'll do the same thing. And there we go. We get that right there. And this, the big point of me finding those two vectors is this. A plane is a span of two vectors on that plane. So you can go ahead and say to yourself, well, if that's the case, that using that fact from geometry, then that set, call this set M, 2/3 minus 1, 1, and minus 5/3 if I have 0, that is a spanning set, okay? And that would also will be linearly independent, okay? So again, with these two vectors and M, you would do the same thing that I did with the previous part of the solution, solution number 1, show they're linearly independent, and you get, yeah, the constant would equal 0. And one thing, let me make this observation, that these answers for M and S, these two bases here that I found, right, they're not the same. They don't have to be. But what you can do is you can get from one, there's infinite number of bases for a vector space or a subspace, but you can get from one to the other. You can write any vector in here as a vector over there. And yeah, that kind of like layman's terms, kind of showing you, yeah, these two are bases for the set, okay? And yeah, that would be it. So I'm gonna do another problem with polynomials, but that will come later on because I don't want to drag this video more than it needs to. All right, well, thanks for your time.